So welcome everyone. I'm Mehreen Mahmood, and on behalf of the Exeter Prize Committee, a very warm welcome to all of you to celebrate this year's prize. Before I begin, just a reminder that the event is being recorded and it will be posted online. So the Exeter Prize awards the most outstanding article published in a refereed journal in the previous calendar year, in this case 2020, from the fields of experimental economics, decision theory, and behavioral economics. This year, we received over 40 nominations for consideration for the prize across a wide range of journals. We would like to thank all the academic staff at the economics department at Exeter who helped us review and help the committee shortlist the papers. And also a very special thank you to Gwyn Carter for her excellent administrative support throughout this process. These shortlisted papers were then passed on to our panelists. A huge thank you for their time in considering these 5 shortlisted papers. The panelists this year were Professors Nina Mazur from Boston University, Rosemary Nagel from Pompeu Fabra, and Thomas Schwesky from Harvard University. And the shortlisted papers this year were What Makes a Rule Complex by Oprea, which was published in the American Economic Review, God Insures Those Who Pay, Formal Insurance and Religious Offerings in Ghana by Oriel, Lesibi, Fanine, Reber, and Seabright, published in the Quarterly Journal of Economics. From Extreme to Mainstream, The Erosion of Social Norms by Bernstein, Agorov, and Firen, published in the American Economic Review. A Model of Competing Narratives by Elias and Spiegler, published in the American Economic Review. And finally, The Dual Accumulator Model of Strategic Deliberation and Decision-Making by Goldman, Bhatia, and Kane, published in the Psychological Review. At this point, if Alex, is Alex here, or should I, she is here. Great. Sorry, I wasn't sure.
I have gotten here.
Great, thank you so much. We're really delighted that the acting Pro-Vice Chancellor and Executive Dean of the University of Exeter Business School is here with us. And I will hand over to her now to give a brief history of the prize and to introduce the winning author and paper. So over to you, Alex.
Thanks, Mehreen. Thank you very much. Oh, that's literally, now you know, hand over to Alex. We have very clear instructions for us. So it's a real delight to be here today. Very excited to hand out my first Exeter Prize today. So the Exeter Prize first started in 2012. This is the 10th award. So it's a special honor to be here on the 10th award. And I think what we really want to talk about is that the papers show a really wide variety of research that encompasses the world of economics these days. I think it's really exciting. And, you know, a wide range of methods you can imagine, plus pure theory. And we are really seeing across a wide range of disciplines from economics, finance management, psychology, which I like to think encompasses the whole sense of the University of Exeter Business School. So I think that's absolutely fantastic. Can we go to, now I feel like I'm giving a COVID briefing. Next slide, please. All right, and I want to actually mention something really exciting about the winner today, Ryan. Oh, and Ryan, please correct me if I mispronounce your name. Oliver gave me training, but I will admit I sometimes do mess these things up. Opera. I believe he is actually the first person to win this award actually twice. Is that correct, Ryan?
I don't know. I have won it before.
Okay, well then, if you've at least won it twice, so I believe that you are the first person to win it twice. So that is quite an honor. And so I'm just going to read a little paragraph. There's an excerpt right here. Is that this paper offers a crisp experimental measurement of complexity. It offers a rich description of how complexity affects actual humans, which has a tremendous potential for informing policymaking as well as theoretical research across disciplines, from psychology, computer science, and cognitive science to economics. In the experiment, the subjects are asked to implement various decision roles. 5 dimensions of complexity are studied: the number of states and transitions, existence of absorbing states and redundant states, and a measure of working memory. The paper looks at 3 different measures of behavior: the error rate, the implementation time, and the subject's own willingness to pay to get the decision rule implemented by a computer. The experiment also measures how fast people learn various decision rules and how transferable this knowledge is. This paper offers a new impetus for research, getting us outside of our comfortable box of constraint optimization. This is a risky and challenging attempt with a high upside. I think it's absolutely fantastic and is really at the cutting edge of the work we're seeing in economics and across a variety of social sciences today. So if we can move on to the next slide.
I think it's now to hand over to Ryan to present.
Oh, so sorry. So Maureen, you're supposed to, so now if I could do the honor of transferring over to Ryan to give his talk. And if you have any questions for Ryan during the talk, you can feel free to put them in the chat box. And thank you for joining us today. It's been an absolute pleasure.
Okay, let me figure out how to share my screens. And in the interim, I'll say I don't know how to pronounce my last name either. If there are any Romanians in the audience, you can tell me. I've always said Opria, so there you go. Thank you for the wonderful introduction, and I'm honored to accept this prize. Let me tell you what the prize is for by talking about this paper, what makes a rule complex. I'll start with an observation that that may not be completely obvious. A lot of human behavior, including in economics, including in economic theory, involves following rules. So when we model people making strategic decisions, we model them as following strategies. And strategies are just rules that describe how actions should flow out of information, preferences, and history. When we model people making intertemporal plans, we describe intertemporal policies. And those are, again, rules that we expect people to follow, to implement themselves, describing how their behavior is going to evolve as information comes in, as events occur, as states change. When we model people making agreements, we model them as contracts. Contracts are rules that describe what should happen in contingencies. Organizational routines are rules, norms are rules, laws are rules, regulations are rules, and even in individual decision-making, if we try to describe how a person goes about making a decision instead of giving an as-if description, we're describing how a person step by step goes through the pieces of information and the considerations involved in making the decision, use a decision procedure. That's a rule too. And if you start thinking about things this way, a lot of social behavior looks like rule following of one form or the other. And I'll make another observation. We don't know that much about how people respond to rules. We don't know, for instance, what makes one rule more difficult to follow than another, or what makes one rule more costly, more painful to follow than another. So these are the types of questions I want to set out to start answering. I don't think I answer them entirely, not even close, but I hope that this research inspires a literature to investigate this to the degree that we think that that proximal decision-making involves choosing between rules. Understanding these questions are of first order importance. So these are the types of questions I want to ask. I want to ask, what types of rules are difficult? What types of rules are costly? What types of rules do people dislike or avoid? And then crucially, is there some sort of systematic structure shaping the answers to these questions? Are there generic features, formal features of rules that make rules more difficult regardless of context, or make rules more costly regardless of context? If we're able to find such structure, we can fold rule following and preferences over rule following into economic theory and use it to build better policies and make better predictions. Okay, so the broad research question I want to start answering here is how much of behavior is shaped by preferences and competencies over algorithms, okay? Where an algorithm is a formal description of a rule. Okay, so I'll make another observation. One thing I think most people can agree on how people what types of rules are difficult, what types of rules people dislike or avoid, is that people don't seem to like complex rules procedures. If we sort of inventory the things we've learned from behavioral and experimental economics about how people fail to behave as economists expect them to, over and over again, we find evidence that people are choosing simpler than optimal rules to make decisions. And this happens both internally and externally. So in terms of internal procedures, the rules we use to make our own decisions, in the repeated prisoner's dilemma literature, we find that subjects use simple rules like the grim trigger strategy. They don't use monstrosities like 2 tit for 3 tat. And that's a bias towards simplicity. In individual choice, making choices over lists, when we regularly observe people failing to optimize, and instead we see people satisficing. Satisficing is just a simplification of optimization. In learning, people use simple reinforcement hill climbing type rules, not Bayesian updating. In evaluating lotteries, people narrowly bracket. That's a simplification of optimal broad bracketing. In planning and intertemporal choice, people tend to be myopic. Myopia is a simplification of the types of intertemporal optimization rules that we think are normative in economic theory, and on and on and on. Okay, so there's this bias towards simplicity. Well, it may be a bias towards simplicity. And then if we think externally, in terms of not the decision rules people use to decide how they're going to behave, but in terms of the external rules that compose institutions, we have lots of evidence that people edit or avoid or fail to comply with complex taxes and regulations and mechanisms we economists design, and so on and so forth. And it may be that the reasons that people are behavioral and the reasons that institutions fail are related, and that they're related by this observation that people don't like or are not good at complex rules and procedures. Now, there's a theory literature, and I'm going to use this theory literature as a sort of beginning scaffolding for asking questions about people's preferences and capacities over rules. And this is, I'm going to refer to this as the automata literature. This is a literature that formalizes rules, for instance, strategies and repeated games. That's where this literature got its start, as algorithms. And the idea is to formally describe a rule as an algorithm. What this literature is focused on is the simplest type of algorithm described in computer science, finite state machines or finite automata, which are at the highest or coarsest level of the Chomsky hierarchy of languages for describing algorithms. And what the literature does is it poses hypotheses about what formal features of these algorithmic descriptions of rules make the underlying rules complex. And what this literature means by complexity is costly. So I'm going to use this literature and its hypotheses as a starting point for asking the types of questions that I just motivated. Okay, so there's a reasonable amount of theory on this. There's almost no empirical evidence directly asking questions about what makes up the complexity of rules. I want to, before kind of talking about my approach, I want to make the case for why this question is worth studying empirically. And this is kind of a recap of what I just said in the last slide. I think there are two big reasons. One is behavioral. I think procedural complexity, the idea that people don't like or are not good at performing complex rules, is one of a handful of potential unifying explanations floating around for the wide range of non-standard behaviors we document in behavioral economics. I'm not claiming that this is the unifying explanation, but I do want to say that before we can even ask whether aversion to complexity could serve as an explanation for lots of disparate things in behavioral economics, we need to first know something about how to operationalize complexity. We need to know how to measure it and evaluate it and make predictions. And this is very hard to do without empirical evidence. And so the type of research I hope this paper inspires would go about building tools to let us ask questions about whether this can serve and how broadly this can serve as a foundation for for lots of things in behavioral economics. The second reason is institutional. If we want to design institutions that work as intended, we need to learn what makes a rule simple and what makes a rule complex. And we just don't have very strong bases for judging one rule as more complex or more simple than another. And so this studying this directly empirically could be helpful for this. So what I'm going to talk about today is a very weird experiment. I want to motivate the weirdness. Instead of doing what we normally do in an experiment, which is give people a choice environment and observe how they make decisions and then make inferences about what drives those decisions, I'm going to give people very alien exogenous rules. And the reason I'm going to study their preferences over these things that I assign them. There are two reasons for this. One is if I just give people a familiar choice environment, I'm going to invite people to bring into their decision-making automatic familiar procedures and heuristics from life that I don't get to observe. And for that reason, I'm going to study a really abstract, kind of almost alien environment. And the second problem is that it's really hard to tell what procedures or what rules, if I just observe people making decisions in a decision problem, subjects are attempting or considering. So I'm going to assign rules exogenously to subjects. And if
Ryan, are you taking questions?
I don't know. You tell me. Organizers, am I taking questions?
We were thinking we'll have Q&A at the end, if that's all right.
Okay.
Thank you.
Okay. I follow rules. So if you agree that these are serious concerns, I think you're stuck with an experiment like the one I ran. And this experiment consists of two types of tasks. One I call the implementation task. And here I just pay people to correctly implement a variety of abstract rules in response to a sequence of 20 events. The way this works is I show subjects one at a time a sequence of letters that are randomly generated that I call events. Sorry. And the subject's job is after they see each letter, they have to type a letter of their own. And that letter I call a choice. And what letters should the subject type on their screen in response to these events? Well, I give them a rule to tell them what to do. Okay, so this rule says choose K until you see H, after which switch to I, then after you see F, switch to K, then after you see another F, switch to I, then start over after you see H. And given a sequence of events and given a rule, there is a unique set of choices that complies with the rule. And if the subject makes that unique sequence of choices, I pay them money. And otherwise I pay them nothing. That's it, that's the task. And what I'm going to do in the experiment is vary this rule. And I'll explain how and why I vary this rule later on. But by varying this rule, I can study things about what makes one rule more desirable than another. Okay, the second part of the experiment is the elicitation task. And here I just elicit subjects' willingness to pay to not be asked to play the same rule again in the future, right? And the way I do this is I give people a maximally simple rule. This couldn't be simpler. Choose N for the entire round. That means type N 20 times. If you do that, I will pay you $2. And on the right side of the screen, I show them one of the 14 rules they've just implemented. And I ask them to tell me what's the minimal amount you'd have to be paid to be okay with being assigned this much more complex rule than this maximally simple rule. By doing this, I can get a measure of how much money subjects are willing to leave on the table to avoid complexity. And this is a measure of cost. And this measure of cost is more or less what the automata literature means by complexity. Okay, now, so what does complexity mean? I'm going to be taking a stand for the purposes of this paper on an interpretation of complexity. When we use the word complexity, we use it in a wild variety of ways. This is part of the problem. We don't have an operationalization. But in computer science, complexity means something very specific, and it means something specific that economists should be really into. Complexity in computer science is a metric of the resources a computational device has to expend in order to complete an algorithm. And computer science usually talks about two types of complexity. One is time complexity, which is the time or the number of steps required to complete the algorithm. And the other is space complexity, which is the amount of working memory that the computer needs to, the computational device needs to tie up in order to complete the algorithm successfully. And so these are types of costs. These costs are what computer science means by complexity. For humans, we might want to add another one. This is the one I'm going to be most interested in. I'll just to make up a word, I'll call it hedonic complexity. This is the well-being a person needs to sacrifice to complete an algorithm. This is the painfulness of performing the algorithm. And if you put all of these together, you have, under some weighting, cost complexity, which is what the automata literature has been focused on. This is a measure of the costs of the opportunity cost of time and the likelihood of making a mistake because of memory overload and just the sheer distaste for the complexity of the rule. In my experiment, I'm going to be able to measure several of these, or at least things that are related to each of these. I'm going to directly get a measure of cost. I'm going to get measures of how long it takes to perform algorithms. And I'm going to get something that might be related to space complexity, which is the mistakes rate. And from this, I can back out how much of this is hedonic. So that's what I'm doing. What am I not doing? This is very important. I am not claiming to model or measure cognition. I'm not testing whether automata are good models of thinking. I am using automata purely as a way of taxonomizing rules for the purposes of measurement. I want a way of describing what's different between one rule and another so that I can study which of those differences matter from a perspective of complexity. I am not proposing a substantive model of the thinking process. This is descriptive. I'm going to skip talking about this in much depth because I just found out that the talk's 30 minutes. So let's just skip that for now. Okay, so what's an automata? An automata is a way of formally describing an algorithm. There are many formal ways of describing any given algorithm. There are many ways of describing any given rule. This is the simplest. And one of the things I'm going to study in the paper is whether this maximally simple way of formally describing an algorithm is sufficient, whether it's sufficiently nuanced to pick up human complexity responses. Okay, so start with a rule. This is an actual rule I give subjects in the experiment. Choose X until you see B, at which point switch to Y. Then start over if you see A. Okay, so I want to model this as a finite state machine. This starts by describing a set of states. And usually when we draw pictures of finite state machines, states are circles. Okay, so these are two states. You only need two states to describe this rule. And each state prescribes an output or an action. So if you're in this state, you should be typing X. And if you're in this state, you should be typing Y. There are a set of transitions between states. And those transitions are triggered by inputs or events. So what this rule says is start in this state, choose X. If you see A's, keep choosing X. But if you see a B, switch to this state and you'll start choosing Y. And then if you ever see an A after that, start over, start the whole rule over. And this is just the simplest description of this rule. Okay, this rule you might recognize is algorithmically equivalent to tit for tat in a repeated prisoner's dilemma. Start out by cooperating. If you see a defection, move to this state and start defecting. But if somebody cooperates, you start over. And this rule, which is equivalent at the level of algorithms to tit for tat, is equivalent to lots of other things you might do in other contexts as well. Okay, now so here's another rule. Choose X until you see A, after which switch to Y, then after you see B, switch to X, and after you see another B, switch to Y, then start over after you see A. And the question is this more complex than this? It seems like it to me. And if I were to try to write down the simplest finite state machine that formally describes this rule, it would look like this. There's more stuff in it, right? So compared to this simple diagram, it has twice as many states, it has lots more transitions and so on and so forth. And what I want to ask is this more complex? And if so, how and why? And in what sense? And those are the types of questions I claim I can get to with the experimental design I sketched earlier. Okay, there's lots of hypotheses. Some of them come from this automata literature about what makes one finite state machine, one rule more complex than another under the lens of finite state machines. The most popular by far is called state complexity, or sometimes it's called S complexity. And this says that when you add states, rules become more complex. What is a state? A state describes, most importantly, the information processing required in performing the rule, the number of distinct ways you have to interpret events and respond to events. But it's also the only way a finite state machine can account for memory. So when you add a state, it says, if you have to remember things from history, the only way to encode that in an automata description of a rule is by adding a state. So states actually have two meanings in a finite state machine. Another theory that's been mentioned in the literature is T complexity or transition complexity. And this is the number of transitions. The way I'll measure it is the number of transitions in excess of the number of states. And this is a description of another burden provided by a rule. It's the amount of monitoring required by the rule. Right? Every time I add a transition, there's an additional possible way I have to respond to an event. And even though states and transitions, these arcs and these circles, are the basic building blocks of an automata, it may be that more than raw state and transition counts matter. It may be that the architecture, the way that states and transitions are arrayed against one another, drives complexity. And so, for instance, this rule here has 4 states and 3 transitions in excess of the number of states, but so does this rule. The difference between the two is this rule is a line that terminates at some point, whereas this rule is a circle that never ends. You could imagine that this architectural fact drives complexity as well. Okay, in addition to these structural hypotheses, I'm going to study a set of deeper and more subtle, what I'll call representational hypotheses. These are hypotheses that are implicit in the automata literature, but that are very important for interpreting complexity. So I'm not going to talk about these now. I'm going to talk about them a little bit later on when I actually get into the data. Okay, the experiment consists of 5 stages. I start out by giving subjects all 14 rules in a random order and ask them to implement them. That means they have to type a total of 280 characters. And I pay them $4 if they perfectly implement the rule. Stage 2, after the subjects have performed all 14 rules, I elicit their willingness to pay to avoid being assigned each rule in stage 3. Okay. And then in stage 3, subjects have to pay off, I pay off the elicitation. Some subjects I randomly assign to rules, and for those subjects, I can study the effects of learning on complexity. And that means in stage 4, I do another elicitation on the rule the subject just spent all of this time playing over and over and over again, and I study whether familiarity reduces complexity. And then stage 5, I have to pay off that elicitation. That's the design. Okay, now what rules do I study? Well, I'm going to, in the design, I systematically vary the number of states and the number of transitions in excess of the number of states. So each of these cells has rules assigned in the experiment. And I use this nomenclature of 2S, XS, YT, where X is the number of states and Y is the number of transitions in excess of the number of states. And sometimes I have a little A after that. If there's a little A, that means that the rule is linear, that it contains an absorbing state. And then I have a bunch of other rules that don't follow this naming convention that I use to study representational hypotheses. So these are designed to compare within cell instead of across cell. So the point is I'm trying very hard to control transitions and states whenever I study other theories that don't have to do with transitions and states. Okay, so let's go right into the data. Subjects. I'm going to show all 275 subjects from the experiment. This experiment was run at UC Santa Barbara. On the y-axis, I have my measure of cost, the money subjects are willing to leave on the table to avoid being assigned the rule. I'm going to show a dot for every subject showing their average cost based on elicitations over all of the rules. So I'm going to bin these guys by the number of mistakes they made at the beginning. So these are 0 mistake subjects, and these are 1 mistake subjects, 2 mistake subjects. You can already see from the sizing of these bins that subjects don't make very many mistakes here. That's really important for the interpretation of willingness to pay. I'll argue that later on. But the median subject only makes 1 mistake over the 280 letters I asked them to write. So these are not hard in the sense that they're difficult to get right. Most people get most of the rules right. But even though they're not hard, in some sense, they're very costly, right? So even subjects who make very few mistakes are willing to pay a lot of money relative to the stakes of the experiment. Each of these dots is a subject. Some subjects are willing to pay nothing to avoid the rules. These subjects might even prefer complexity, but they're in the minority. Most subjects are willing to pay a considerable amount. And then crucially, I'm going to draw lines for each of these dots showing the range from least complex to most complex. And you can see that most subjects make huge distinctions across rules. And so most of the subjects are not treating all of the rules the same. They view some rules as more complex than other rules. And the question I'm asking in the paper is whether there's structure in this variation, right? Whether they're principles that predict these ranges of costs. So here I'm going to just make this complex figure even more complex by showing for each of these subjects the average implementation time, the average amount of time it took the subject to implement the rule. And the thing I want you to notice is there's almost no relationship between the cost I'm measuring and the amount of time it takes to perform the rule, just as there's very little relationship with mistakes. Okay, and that means that what I'm picking up here is largely a preference rather than something having to do with time or something having to do with mistakes. Okay, so let's talk about this variation. Let's talk about whether there's structure underlying it. We'll start with the structural hypothesis. We'll start with state complexity. Okay, so all of my results come out of a big monster regression reported in the paper that I'm not going to talk about here. I'm going to show examples instead that illustrate what the results look like. Okay, so the first theory, the big theory, the one that's most often talked about in the literature is state complexity. And I can study state complexity by controlling the number of transitions. So looking in this row, I'm controlling it 2 transitions and varying the states, 2s2t, 3s2t, 4s2t. And I can look at whether the cost response, and I can also look at whether the time and mistakes response changes as I add states, holding everything else constant. Okay, so this is the rule 2s2t, which contains 2 states, and the rule 4s2t just sort of crams 2 states in between. And now, of course, I'm not showing subjects these automata. I never mention automata. I'm giving the simplest verbal description of these rules I can. Okay, so on this graph, I'm showing the total transitions. That's the number of states plus the number of transitions in excess of states. And here I'm showing cost. And the thing to notice here is that as I add states, cost goes up. Okay, here is the closest I'm going to come to showing you a regression table. I'm going to show you based on estimates from my regression, the percentage effect on cost of adding a state and the percentage of effect on time. And what this says is that adding a state adds about 20%. Every time I add a state, I add about 20% to the complexity costs. And I add about 20% to the amount of time it takes to follow the rules. I could do the same thing with transitions. Hold the number of states constant and add transitions. So this rule 4s2t contains 4 states and 2 transitions in excess of the number of states. This rule 4s4t adds transitions. And adding these transitions means that the subject needs to monitor the environment more intensively in each of these states. Okay, so here's what I showed you before. So let's add those 3 diagnostic rules to measure transitions. And you can see as I add transitions, that adds cost as well, but it adds less cost than adding a state. In fact, the slope's about half the size. Okay, going back to my regression, indeed, when I add a transition, I add about 10% to cost. It actually doesn't have any effect on how long it takes me to follow the rules. And last, we can look at architecture, or does an absorbing rule change complexity costs? Here I have two rules that have the same number of states and the same number of transitions, but this one terminates, this one doesn't. And I can look over all rules that contain an absorbing state, and you can see that there's just sort of a downward shift in cost when there are absorbing states in a rule. And turning a rule to an absorbing rule reduces costs by about 20% and has a much bigger effect on time. Okay, so now the deeper hypotheses in the paper are the representational hypotheses. Tell me when I need to stop talking and I will do it. Okay, the representational hypotheses. These have to do with how people represent patterns of behavior to themselves as rules. And we can actually study this to some degree in this experimental design. There are two implicit theories about this in the automata literature. One of them I call efficient reduction, which is an assumption that people don't overcomplicate descriptions of rules themselves when evaluating complexity. If a rule contains unnecessary states, people sort of are able to edit out the complexity of those additional states. So if I can write down a rule in a simpler way than it's described to me, I'm going to treat it as less complex. And another, this one's even bigger, is this literature sort of implicitly assumes that a finite state machine representation is sufficient to describe the complexity of a rule. And so that's implicitly an assumption that people represent rules in an automata-like way. And the experiment can assess both of these hypotheses. So let me just go through that.
Ryan, if you could wrap up in 5 minutes, that would be great. Thank you.
Oh my, okay. Okay, this rule 4S4T is not reducible. This is the simplest description of this rule possible. This rule reducible, on the other hand, can be reduced in the sense that instead of following this rule, I could follow this much simpler rule, and over any possible history, it would give me the exact same actions. So that means this rule contains redundant states. And by comparing behavior in 4S4T to behavior in reducible, I can discover whether this assumption that people efficiently reduce works. I also give subjects the rule reduced directly, and I ask whether they behave similarly across these two cases, which efficient reduction would assume. The answer is no, people don't reduce machines at all. And I even have some exercises in the experiment where I let them play this over and over and over again, and they just sort of never get it. And they treat the reduced version of the reducible rule as far less costly. Okay, the other big thing that I do on representation in the paper is I study the most important assumption in the finite state machine representation, which is that people treat memory kind of the same way and with equal weight to the way they treat information processing. And this is the sense in which a finite state machine is not nuanced, in which it has a kind of descriptive poverty. And so we can always go to more complicated descriptions of algorithms to separate out these rules. We can study whether this really simple description is sufficient. So this rule 4S4T, states exist entirely to the information process. The point of a state in each of these cases, not entirely to track memory, it's to track memory plus to decide how to interpret events. This rule countable, states exist only for memory. What this rule countable says is wait until you've seen B 3 times before transitioning. So you can feel the difference in complexity across these two uses for states in the sense that 4S4T, when I describe it to subject, the simplest way to do it is to say, choose X until you see A, then switch to Y, then switch to B, or switch to X after you see B, then switch to Y after you see another B, and then start over if you see an A. But this rule countable, you can describe to subjects as choose X until you've seen B 3 times, and then start over if you see an A. It's simpler. The reason it's simpler is because the information exists, or the states exist entirely for memory purposes. Okay, so you can actually go one step down in the Chomsky hierarchy to a more sophisticated description of algorithms called the pushdown automata, that in addition to having states and transitions, holds a string of characters in working memory. And by doing that, it pulls apart the memory role and the information processing role of states. And under a PDA representation of this countable rule I just described, the rule only has two states, and it has very few transitions. So this is the simplest way I can formally describe the countable rule under a finite state machine representation. But if memory and information processing are meaningfully different, you can describe it more simply. Okay, and so I just do the same exercise I did before. I compare 4S4T to countable. Countable is way simpler. And that strongly suggests that we should be using more sophisticated descriptions of algorithms to taxonomize rules than finite state machines. And the paper goes into this in details about how we might go about doing this. One of the things you should get from this is that this paper is a kind of crude first step in what could be a much more sophisticated and interesting research agenda, a sort of quest for a really good algorithmic description of the complexity of rules. And I hope this paper is eventually forgotten, and a really great paper that does a much more sophisticated job using more sophisticated descriptions of algorithms ends up being the touchstone of the literature. Okay, since I'm supposed to be stopping, I'll just show you slides that look interesting, and you can go to hopefully these whet your appetite to go read the paper. There's all kinds of interesting stuff happening. I'll skip that. I give subjects lots of experience with some of the rules, and I study whether that familiarity with the rule reduces complexity. It does. There's a huge learning effect, like 30% reduction in cost if you've been playing a rule a lot. Okay, so people can get used to a complex rule, and then it stops being costly for them or stops being as costly for them. But this learning is extremely shallow if I have subjects get their willingness to pay for a slight variation on the rule that has the same structure but just has different letters. Most of that cost reduction disappears. Finally, I have a version of the experiment in which subjects have to perform the rules entirely in their head. So I show them all 20 events to begin with, and their job is not to write down all of the interim steps. Their job is to figure out what the final action should be if they were to perform the rule on the string. And it turns out that subjects view this as far more costly. They're actually no worse at it. They don't make mistakes at a higher rate, but this is far more painful than using a rule to guide a sequence of actions. Okay, so using a rule to reason is much more costly than just sort of rotely following a rule. Okay, so let me just wrap up by pitching a research agenda I hope everybody gets involved with as soon as this talk is over. There's a long tradition in economics. I associate it with Herbert Simon, saying that there's a kind of algorithmic layer of choice preceding behavior that we usually ignore in economics. That you're not just choosing actions, you're choosing rules to guide actions, and that we might have preferences over those rules. These choices over rules are at least in part governed by complexity intuitively, and that's what my paper suggests, is these costs are real. Most importantly, preferences and capacities over algorithms seem to have structure. So there's a lot of structure in what makes one rule more complex than another. And because it has structures, we might be able to map it, and we might be able to enshrine it in theory. And we can, if we were able to do that, this is a joint empirical theoretical research agenda, we could use it to understand how we go about building institutions that work the way we want them to, and also to understand and anticipate when we should expect people to not behave as we expect them to. Okay, that's it. I'm done.
Great, thank you so much. And apologies that the rules today have made you cut short your talk, but we hope that the discussion that's going to follow will make up for it. We are delighted that Guillaume Frechet from the New York University has joined us today to discuss this paper and the topic more broadly. So over to you, Guillaume. If you could stop sharing your screen, please, Ryan.
Oh, yeah.
Hello, everyone. Thank you for inviting me to discuss this paper. So I'll try to go quick so there's some time for question. My discussion is not so important. But what makes a discussion simple is a great paper. So then there's not so much to talk about. This project reminds me of years ago. I had two students, Emmanuel Vespa and Alistair Wilson, who came to me with a project on, it was sender receiver games with multiple advisors and multiple dimensions. And they described to me the project. There were all sorts of challenges in terms of going from the theory to the lab. And I said to them at the time, yeah, sure, this is a great question. It's obviously great and interesting. There's just no way you can take it to the lab in a meaningful way where we'll look at the data and think we've learned something. And then they went and did it. And then I was jealous I didn't come up with it myself. And this is how I feel about this paper. It's obviously an interesting question. And when I first read it, I thought, when I first read just the start of the paper, I thought, wow, this is interesting, but there's no way you can do this. And then I'll like what I see. And I was wrong, and then I wished I had written the paper myself. Okay. So what makes this paper good, in my opinion? I'll go over just parts of it and then kind of highlight how it resonates with me. So first, there's one motivation for this, which is just from the theory perspective. Clearly on the theory side, in some games, automaton can be useful. They offer a natural way to have implementation costs, which is going to give you equilibrium selection when there's multiple equilibria, and that can be useful. So there's a paper by Baron and Calais, where they look at a multilateral bargaining environment like the one from the paper of Baron and Fairjohn from '89. And in the Baron-Fairjohn setup, you have an infinite number of subgame perfect equilibria. And they use a kind of automaton approach with complexity cost to select a unique equilibrium, which is the stationary subgame perfect equilibrium. Now, in the paper, they write, simplicity of an equilibrium is a difficult notion to define. Okay, so that's kind of, oh, yes, maybe we'd like to go with simplicity, but we don't know how to do it. And then they essentially say, oh, look, let's have automaton, and then boom, we all agree, count states, that's complexity, we move, nobody disagree. It's kind of obvious once you've got this notion how to move forward, and they get equilibrium selection. But other authors have come to the same problem and said, oh, look, we need the complexity, let's define automaton, count transitions, boom, we move along and get equilibrium selection. Well, those two things are different. So like in both cases, they move along as if it's obvious, but they've moved along in different ways and they're going to get different answers. And so it seems to be a natural question. Well, if we could somehow look at behavior and see what do they react to states or to transitions or to something else, then maybe we can speak to theorists and tell them, well, if you're going to do this, the criterion you want to use for complexity is this one, not that one. Okay, so that's an interesting motivation, I think a very natural one. A different motivation, and this is the one, now I teach this paper in my graduate class, and this is how it fits in my class. In different settings, automaton are a natural way to represent strategies, and in particular in repeated games, okay? And if you look at, say, the automaton on the left, that's a representation of a Grimm trigger strategy. And the automaton on the right is a representation of a different strategy, a tit for three tat strategies. And, even without anything fancy, this looks more complex than that. There's certainly more states, okay? Now, when we look at data from these experiments, what we see is that under perfect monitoring, we find automata that look like this being played by people. The way people play is consistent with automata that look like this. But when we have environments with imperfect public monitoring, we see automata that are more similar to this being selected often. Now, not this one in particular, I just copied a figure from Ryan's paper, but so slightly simpler than this, but still many more states than that. So when you see this result, at least one way I make sense of it is the following, is that under perfect monitoring, if we use strategies like the one on the left there, we can support full cooperation. But in an environment with imperfect public monitoring, an automaton like the one on the left will not support full cooperation. It's going to have actually not that much cooperation, because often you'll see signals that the other one defected, even though he cooperated, because in equilibrium, maybe he's trying to cooperate. You'll see defects that's going to trigger punishments. Whereas if you use a strategy more like the one on the right, you'll be able to support more cooperation. So that could make sense in a world where people have a preference, or it's easier for them to use the simpler automata or strategy. And so they only deploy more complex one in environments where it has a benefit. If it has no benefits, like in an environment with perfect monitoring, why use something complicated? Let me use something simple. When I'm in an environment where there could be an upside to using something complicated, then I deploy something that's more costly because there's a benefit. That to me is a story that makes sense, but until you have somebody that goes and measure how people, the cost for people of deploying these automata, then it's just a story, okay? And so Ryan's paper is a way to really approach this and put some meat on the bone and see whether this is a story that makes sense. He does it in a very clever way, in my opinion. This implementation on the left, the way described the rule in words, and then to have these simple sequences of letters. I would have not come up with this, but I think it's great. And then he gets the valuation from people. And then he has this experimental design in 5 parts that has all sorts of, you can see thinking behind it that's useful ultimately. You first have them play many different rules. Then you get the valuation for all of those. Then you get them to play a lot with one rule. So now I can look at not only a cross section, but I can look at also experience and think about learning, and I get again valuation. So there's all sorts of bits and pieces of that design that I think show a lot of cleverness and usefulness ultimately. Now, so far what I've told you is that he's got a good question, a nice task, and a good design, but then he also got lucky, which is half of a good paper, which is he got super clean results. Okay, so state complexity increases cost by 20%, transition is half of that, and an absorbing state reduces complexity by about 1 state. These are all very easy to state results that make sense once you see them. You don't know this ex ante, but exposed, they make sense. You can see the ordering of the complexity is pretty clear. And so he got lucky on a good question with a good design. That's a recipe for success, I think. Now, in terms of, so this prior result really speaks to the first motivation I gave. With respect to the second motivation, he takes those costs and then maps them into strategies that are popular in the repeated game literature to see what cost those strategies would entail. And what you see is that strategies like always cooperating, always defecting, GRIM, or tit for tat, they're all very low cost strategies. And those are the strategies we see people use in perfect monitoring environments. And then strategies like GRIM2, TF, tit for 2 tats, and GRIM3 and 2 tits for 2 tats. These are all strategies we see in imperfect public monitoring environments where there's value to using those more complicated strategies. And so it makes sense that people would use stuff that's more costly to them in environments where there are benefits to using them. So to finish, I think it's a great paper for all these reasons I've said. I also think it generates all sorts of interesting new questions. I won't, I'll go really quickly so people can talk about what they want. But I think there's question that it opens about how do people trade complexity versus other aspects of their preferences. There's also how, can you take any of these results beyond automatons? Does any of these features of complexity translate beyond automatons? And then, and this is not what he goes into at all, but I have a question that seems interesting to me is when are automatons useful approximation for behavior? Are there settings that we can delineate where automatons is a good way to think about how people behave and others where they're not? and that's it. Thank you, Ryan.
Great, thank you so much. We have some time for Q&A now. I'll go first to Ben, who had a question in the chat, but others, please feel free to raise your hand and we can call on you to ask your question. But Ben, please go ahead.
Hi, thanks, Mehreen. Thanks to Ryan and Guillaume for very, very good, clear presentations of the paper and the implications. This is a question that really sort of came up in my mind towards the beginning of the talk, and in a way you answered it, but in a way I also think it would be nice to come back to it now, which is, are you thinking about rules as purely the outcome of an optimization problem, meaning a rule of thumb that you come up with on how to proceed, or are you thinking about it as the outcome of a constrained optimization problem, where the constraint may be imposed by the play, you know, how another player plays, but it may also be imposed by a constraint that you want to impose on yourself. So it would be, you know, this would be the idea that you'd actually implement you'd constrain yourself as part of a self-control problem. And it seems to me that in both of those second settings, you'd being having the rule as simple is at a premium, because you're either communicating to somebody else or you're communicating to yourself, and you want to be absolutely clear. You know, there's a premium to being clear what you're responding to, as against when it's yourself. I mean, it almost seems to me that when you're playing against yourself, you can see situations in which you actually take pleasure in additional complexity. You know, if you're cooking a recipe, or you're building a model, or you're the complexity is at a premium. So I just wondered if you'd thought about that as you were going through this, and how you would suggest how we should be thinking about the framework that you're setting up.
Yeah, so let me, there are a couple of questions in there, so let me just sort of answer some of them, and you tell me if I'm missing any of them. What I think I'm measuring here is one outcome of complexity, which is a kind of just sheer subjective cost. And what I would hope is that this can enter into decision-making, optimization decision-making, for instance, or choosing how to best respond, et cetera, in the way any other cost does. I mean, that would be obviously the best thing for economists, given how we like to model things. This is the idea is that there is, that behavior itself is costly, and that one of the drivers of this cost is something that we could call complexity. And how this folds into a deeper optimization problem, I have no idea based on the data I have so far, but I hope in a simple way. That would be the best for social science, but maybe not. It may not be. Now I'm measuring one type of complexity. I call it procedural complexity in the paper. There are other types of complexity we might be concerned about. For instance, we might be interested in what's the complexity of inferring something. So for instance, I could have run an experiment. In fact, one of my co-author and I, Chad Kendall, have a follow-up paper where we do this directly, where we ask what makes it difficult to infer a data generating process determined by describable by a finite state machine. And that complexity could be different. It could be driven by different principles. And you could go on from there. There are probably many different ways in which we need to use a word like complexity, and asking questions about the relationships and unity across those things is an agenda. Now, as to your last point, or last question, don't I think it's weird that people sometimes don't like complexity and sometimes do? Yes, I think that's weird. But I also think it's weird that people hold insurance and also go to casinos. And I think it's probably a similar type of thing. About 10% of the subjects in my data set are willing to pay nothing to avoid complexity. And I can't rule out the possibility that these people are going to be accountants in the future, and that they are just, that they love complexity and they're willing to pay for it. I tremendously enjoyed writing this paper. It was one of the most pleasant things I've done in my life, but it was incredibly complex. So there you go.
Interesting. Thank you.
We're over time, I realize, but I hope it's okay, Ryan, if we take a few more questions.
Yes.
Yeah. Julian, do you want to go ahead?
Sure, thanks. And no comments on the complexity of the wallpaper behind me, so I'm not going to go there. I'm not going to make any jokes about that. Thanks, Ryan. That was really great. So my question was about, you mentioned the verbal descriptions, and you're trying to sort of pin those down in as simple as way as possible. So I started thinking about the complexity there, and I think really it's two questions. So one is, do you feel like there was a pretty canonical way to do that, or do you think there were choices and that might change things? And then the second one is, let's set that aside and assume you did that, or it doesn't matter. You could purposefully complexify there as well and say, well, look, you start in this state and later on you're going to get to some other state, but we're not there yet, and think through this in advance. I mean, you could make it, you wouldn't want to do this, but you could do that. Do you think that would introduce, presumably it will introduce some costs. They won't like that, but is that going to be the same kinds of costs? Are they going to learn? I know you didn't have a lot of time to talk about the learning stage, but is that going to get stripped away in the same way that reducibility does? So where does the verbal element come into all of this?
Yeah, that's a great question. So I programmed up two completely different versions of the experiment. I had a whole thing set up that described the rules in an automata-like way. So it had steps, and you could jump around from steps, and it was described very crisply. It was really clear how it worked, and then I had this version where I tried to describe as simply as I could in words. And I up until the week before I ran the experiment, I wasn't sure which one to run. I ran the one that I thought was less likely to work. Because I thought that evidence that came out of that would be more convincing to me that automata were, if people respond to an automata description in an automata way, that's not quite as convincing and not quite as useful as a verbal description. But I'm sure that costs would have changed. I hope that the comparative statics wouldn't have changed. I'm sure that the levels would have changed if I described it in an automata way. The way I did the verbal stuff is I had to define words in order to make these things not huge, like phrases that had specific meanings, like start the rule over. I had to use that to describe going back to the beginning of the rule, and I had to train subjects in how to interpret that in order to keep the words from, because I really didn't want subjects to be responding to huge, being aversive to huge paragraphs of reading. I wanted to keep the description short, but that makes this a more difficult experiment to run online. So probably what I should do in the near future is run a replication of at least part of the experiment online, since everybody's doing experiments online these days, using an automata type description, and then we can do kinds of comparisons. But I'm completely willing to believe that there is a separate thing that you might call linguistic complexity. There's a big literature of metrics on linguistic complexity. I'm working on an experiment on linguistic complexity where there's nothing complex going on. The descriptions are just becoming complex in the way linguists think descriptions might be complex. And so that is almost certainly a different layer of complexity that probably follows different rules and that we should be studying as well.
Great, thank you. I think we'll wrap up now. I don't see any further questions or raised hands. So thank you once again so much, Ryan, Guillaume, for joining us, to all our panelists who helped us with this process, and all of you for attending. Thank you and goodbye.